This video is for Unit 4, Lesson 5. This is our last new topic of Unit 4, so the test is coming up soon. Be ready for that. First, I wanted to look at some transformations. So if we have a picture of a function like we have f of x here, without even knowing its equation, we can transform it to other functions depending on what transformation we wanted to make. So this first one, I want to know what happens if I add 4 to the function. Well, if I add 4 to the function, I'm adding 4 to the y value. That's going to shift it up. If it was negative, it would shift it down. But in this case, it's going to shift it up 4 units. So to transform this, what I would like to focus on is these intercepts first. So right now the intercept is at -2. We want to shift that up 4 units. Another intercept is at +1. Again, we want to shift it up 4 units. And the last one is at +4. We're going to shift that up 4 units. In some ways, you could almost think about that you're like shifting that x-axis up to the +4. That still makes it difficult to sketch, though. We need a little bit more points, a couple more points to help us get a good picture. We have this maximum right here. It's right now near here, if I draw it on this coordinate grid. That's also going to shift up 4 units. It's going to be around right here. And the exact location isn't important. We're just trying to sort of eyeball where it's at. And this one here is, it's between 2 and 3 in the x direction and between -2 and -3 in the y direction. It's right around here, and that's also going to shift up 1, 2, 3, 4 units. So using those 5 points now, I can get a pretty good sketch of my graph. So it goes up, hits that maximum, turns around, and it's not my best drawing ever, but it'll do. So that would be f of x plus 4. If I wanted to know what the graph of the function of f of the quantity x plus 4, if that x is being added not to the function itself, but to the x value, remember when it's associated with that x, that's shifting it to the left or right, and in this case, it's shifting it to the left 4 units. So looking at those same intercepts on the original function, they're at -2, 1, and 4. The graph we want to create is shifted to the left 4 units. So the intercept that was at -2 is now at -6. The one that was at +1 shifts over to -3, and the intercept that was at 4 is now at 0. All right, so let's also look at those max, or that relative max and relative min. If it shifts to the left by 4 units, it's going to be around, between -4 and -5 in the x direction. So it's going to be somewhere around here. And that minimum happens between these other 2 intercepts, and it would be somewhere about right there. So now we have those 5 points. We can sketch the function in. And again, that was shifted to the left 4. So if the number is added to the function, that's going to shift it up or down. If the number is added to the x value, that shifts it in the x direction, left or right. Let's look at a couple of stretches now. If you have a function f of x and you want to multiply it by 3, it's not going to change the location of those intercepts. I mean, if you think about maybe a factored form of this equation, and this is probably not its exact equation, but if you multiply it by a number like 3, those zeros stay at exactly the same place. They do not move. So we will still have intercepts at -2, at +1, and at +4. What happens is that uh, that maximum is going to be 3 times as high. It's going to be way up here now. The intercept in the y direction is going to be 3 times as high. It's going to be at 6 now. And this minimum is going to be 3 times as low. It's going to be way down here now about. And again, I'm just thinking about what would be 3 times as high or 3 times as low. So here's our function that's 3 f of x. Negative f of x works the same way, but instead of multiplying or thinking of the heights as being 3 times as high, 3 times as low, we're going to think of them as being -1 times as high, -1 times as low. So again, we have those same intercepts when we multiply it by a scale factor. We still have intercepts in -2, 1, and 4. Instead of having a y-intercept of 2, though, if we multiply it by -1, it's going to be at -2. That max was, just above 2. That's now going to be just below -2. It's going to flip it over, reflect it. And that minimum is going to reflect, if we multiply it by -1, it's going to be somewhere up here. So you have a function that looks something like this now. And you can kind of see it just looks like that original function, but it reflected it over the x-axis. So now we're going to try to write a couple of the function transformations. So here's our original function f of x. Now we are going to be comparing to this same f of x function each time and trying to decide how we think it changed. So the first thing I look for is I look for those intercepts and I see if they are in the same spot. And in this case, you can see that the intercepts definitely changed. If the intercepts changed, you know that it either shifted up or down or left or right. If the intercepts stay the same, you know you multiplied that function by something. Well, in this case, hopefully you can see that that function has shifted up. And if I'm thinking about how far up it shifted, I can kind of eyeball it this way and see that it definitely shifted that function up 4 units. So it's the same function, but shifted up 4 would be a +4. Let's try another one. We're comparing again to the same function. So I usually start by checking my intercepts. And in this case, the intercepts are exactly the same. Well, that means I had to have multiplied my function by some constant number. So then I have to think about what that number possibly could be. Sometimes the easiest way to determine it is to look at that height of your min and your minimum or your maximum. Sometimes there'll be one that's easier to see than others. This one had a maximum at a height of 3. That max is now at a height of 9. So it looks like our function was multiplied by 3. We could check and see if we think that happened over here. It's at like 1.5 in the minimum, -1.5, and here it's at -4. That also looks like it was multiplied by 3. And it was. This one probably was more like -1.3. So when you multiply that by 3, you get -4. So that one is 3 times the function f of x. Let's look at another one. Again, I usually check my intercepts first and mark those. Over here, the intercepts are at -7, +1, and 6. So Thinking over here on this one about how those might have changed, it looks like everything was shifted to the right by 2 units. That's a change in the x direction. If it goes to the right, we would write that as f of the quantity x minus 2. Another one. So again, check your intercepts first. Hey, look, they're exactly the same. If the intercepts are the same, you know that it's a function that's being multiplied by some number. Let's see if we can figure out what that number is. Well, the height of this relative maximum was at positive 3. This one looks like it is at negative 3. So it looks like we multiplied by negative 1. So usually we'd probably just write that as negative f of x, but it's fine if you have the 1 there. All right, another one. Check your intercepts. Negative 9, negative 1, and 4. Negative 9, negative 1, and 4. The intercepts are the same. The end behavior changed though, and this maximum, relative maximum, reflected over the x-axis and became a minimum, relative minimum. So it looks like we have our original function, and we're multiplying it by something, it reflected it. So we know that something is negative. And, you know, the height was around positive 3. It's now around negative 1.5. It looks like it is half, negative 1/2 f of x. Okay, so that's it for the function notation part of it. We're now going to use the real roots of the polynomial to sketch the graph. If the polynomial is in factored form, we're going to be ready to go and start sketching. But if the polynomial is in standard form, we're going to need to factor it first. Again, the reason that we need to factor it is because if it's in factored form or intercept form, then we can immediately see what the roots or the zeros of the function are. So here's the first one. Sketch the graph of the function. Use the real zeros, the multiplicities, and the end behavior to help you. So the first thing that we notice is that this function is in intercept form. That means we can immediately tell what the real zeros are. The real zeros are negative 3. The factor x minus 1 tells us that it has a real 0 at positive 1, and the factor x minus 4 tells us that the function has a real 0 at positive 4. So remember, those real zeros correspond to the x-intercepts. So we can mark those on the graph. Here are x-intercepts at negative 3, at positive 1, and at positive 4. We know our function goes through those 3 points. So we can think about the end behavior. This function, g of x, has 3 factors. That means that it is a degree 3 function. It has a factor here, it has a factor here, and it has a factor here. It's degree 3. If we want to know about the end behavior, we just need to know if that is an even or an odd degree. And in this case, that's an odd degree. And the leading coefficient, we would have to kind of think about, if that was all multiplied out, what would we have for that first term? And that first term would be 1x to the third. So the leading coefficient is a positive number. So we have a function that we know has an odd degree and it has a positive leading coefficient. So we know that the ends are that it's going towards positive infinity on the right and towards negative infinity on the left. So I know as it comes through this intercept here at 4, it's got to go up to positive infinity. And on the left-hand side, as it goes through this intercept at -3, it's got to go down to negative infinity. Now, we can kind of just use common sense to figure out it's also got to go through here at 1, so it must turn around and come up through there and then turn around and come down through that -3 intercept. So this is the basic shape of our function. We need one more piece of information to make our graph complete, and that is that you should mark the value of the y-intercept. So you may or may not have noticed that I don't have a scale on the y-axis. That's because for polynomials that y-intercept can vary greatly. It can be a number between 0 and 10. It can be hundreds or even thousands high above the x-axis. That number just varies so much. So I don't put a scale here, and then we can kind of scale our function by just indicating what the height of that intercept is. So remember, if you're finding the y-intercept, that happens when x is equal to 0. So we just plug 0 into the function for x. 0 plus 3 times 0 minus 1 times 0 minus 4. You could calculate that with your calculator, or you can do it in your head, and you find that it is, I'm going to simplify it a little bit, and you find that the intercept has a height of 12. So mark that on the graph so that we know, it gives us some sort of reference for how tall that function is. All right, so that's the first graph. Let's try another one. Sketch the graph of the function. Use the real zeros, multiplicities, and end behavior to help. All right, so our function is f of x equals negative quantity x minus 4 squared plus 5. So remember that the factors in the intercept form reveal the real zeros. Since we have a factor of x minus 4, we know we have a real 0 at the value 4. Since we have a factor of x plus 5, we know we have a real 0 at the value -5. Remember, those correspond to the x-intercepts, so we can mark on our graph that our function has x-intercepts at the values -5 and 4. Now let's look at our end behavior. So the end behavior of this function, well, we have to think about what degree it is. And we have to decide if the degree is even or odd. Well, this factor, remember that the power here is just shorthand for that factor is repeated, that it has a multiplicity of 2. So we have two factors of x minus 4, and then of course we have a factor of x plus 5. So altogether, this function has 3 linear factors, so it's degree 3, which is an odd number. The leading coefficient in this case, if we multiplied it out, because we have this negative symbol here, that is going to be a negative leading coefficient. So we have a function that has an odd degree and a negative leading coefficient. We know that the two ends on the right are going to be down towards negative infinity, on the left are going to be up high. And I'm just going to kind of really roughly put those in. Now this one's a little bit tricky because we only have 2 intercepts, and we have to remember that this power, the fact that this is a repeated root, causes some unique behavior at the intercept +4. So instead of the function just crossing from one side to the other, the fact that that power is there means that the function is actually going to have a tangent behavior at that intercept. It means it's either going to go up to that +4 intercept and turn around and go down, or maybe it's going to come down, touch it, and go up. And at first, you can't really tell which way it is until you think about that end behavior. Well, since it's going to negative infinity on the right-hand side, that has to be coming up and touching that intercept of positive 4, and then turning around and going down. So you have to kind of use the end behavior to help you figure out on which side of that x-axis the function is. And then this one, of course, is just a regular factor of x plus 5, so it just goes straight through there. And so our function maybe looks something like this. So I want to mark the value of that y-intercept. Remember that the y-intercept happens when x is equal to 0. So if we plug 0 into our function, we get negative 0 minus 4 squared times 0 plus 5. And if we keep simplifying that, which you could easily do in your calculator if you'd rather, looks something like this. That negative 4 squared is a positive 16, and we times that by a negative 1 and by a positive 5. So our y-intercept is at negative 80. So that's our second function. So the purpose there, I wanted to show you that sometimes if you have a multiplicity on one of your roots, you need to be really careful about showing that proper behavior at that intercept. All right, sketch the graph of the function f of x equals 4x to the third plus 20x squared minus 9x minus 45. So this is such a cool problem because it basically is going to use every bit of information that we've learned this unit. So I love it. So f of x equals 4x to the third plus 20x squared minus 9x minus 45 is in standard form. When you look at a function in standard form, there's a couple things that you can tell about that function. First of all, you can tell what the end behavior is. The leading term here is 4x to the third, so that means this function has an odd degree, it's degree 3, and its leading coefficient is 4, that's a positive number. So the end behavior of this function is the odd positive behavior where it's going to positive infinity on the right and towards negative infinity on the left. Okay, so we've got that end behavior from the standard form. The other thing that's really easy to figure out from standard form is the y-intercept. Remember, it happens when x is equal to 0. So if we put 0 into this function, it's 4 times 0 to the third plus 20 times 0 squared minus 9 times 0 minus 45, and that's so easy to calculate because it's 0 plus 0 minus 45. So the y-intercept is going to be negative 45. And we'll just put that over there. I'm not sketching my ends yet because I don't know where the intercepts are. So when you look at a function in standard form, you absolutely cannot tell where the x-intercepts are. Standard form hides that. But if you put the function into factored form, into intercept form, then those intercepts will be revealed. If you have a function in standard form and you would like for it to be in intercept form, you factor it. This polynomial has 4 terms, so the factoring strategy that we're going to try is factor by grouping. So we think about that first group, and they have a 4x squared in common. So we factor that out, and we get x plus 5. And we think about our second group, and we think about what that group has in common, and it has a factor of negative 9 in common. We factor it out, and we get x, and it's a negative 45 here, but if we factor out a negative 5, this also becomes x plus 5. It's working great so far. So we notice that each of these terms now has an x plus 5, so we can factor that out, which leaves behind 4x squared minus 9. Well, that quadratic factor 4x squared minus 9, we can factor just a little bit more. I know you guys love it when we can factor a little bit more. So we have that x plus 5 still. We don't want to lose it. But 4x squared minus 9 can factor as 2x plus 3 and 2x minus 3. 3 and my minus kind of merged. So now that we have it in intercept form, this is intercept form because it's factored. It's in intercept form so we can see the real zeros now. That factor x plus 5 tells me that it's going to have an x-intercept at negative 5. 2x plus 3 is the next factor. Think about solving that in your head. You would subtract the 3 and divide by 2. Negative 3 halves. If you have a fraction and you have a hard time placing fractions on the coordinate grid, you can think about it as a decimal. Negative 3 divided by 2 is negative 1.5. So it would be right in between the negative 1 and the negative 2. And that last factor, 2x minus 3, we would, if we set that equal to 0, we would add the 3 and divide by 2. So that one's at positive 1.5. Okay, we don't have any multiplicities, so we don't have any unique behaviors. We can fill in our end behavior now. We know that as it goes through this intercept here, it's going to be going up because it's positive odd. And as it goes through this intercept here, it's going to be going down towards negative infinity. And we can kind of fill in the rest of it from there. So this is our function, f of x. Let's try one more like that where we have to factor. We want to sketch the graph of f of x equals x to the fourth minus 29x squared plus 100x. I think this is our first degree 4 polynomial to graph. So again, it's in standard form, so we can immediately tell what our end behavior is going to be. Well, the degree of this function is 4, so that is an even number. And the leading coefficient of this function is just 1. So that is a positive number. So the degree is even, the leading coefficient is positive. That tells me when we sketch it that both ends are going to go up towards positive infinity. We can also immediately tell the y-intercept. Remember that happens when x is equal to 0. If we substitute 0 in for x, we get 0 to the fourth minus 29 times 0 squared plus 100. So our x-intercept is going to be 100. All right, well, to find out where those intercepts are, we are going to have to put it into intercept form. We're going to have to factor. Well, this polynomial has just 3 terms, so we're just going to try some regular factoring. These two leading positions have to multiply together to give us x to the fourth. So we're going to have an x squared and an x squared. And on the other end, we've got 100. So we need to figure out which of the factors of 100 we want to put in these two positions so that we can somehow get a negative 29x squared. Well, 100 might be hard for you to think about. Just try things until you find the right combination. But in this case, we're going to use negative 25 and negative 4. Negative 25 times negative 4 multiplies to positive 100. And the negative 25x squared and the negative 4x squared will give us the negative 29x squared. All right, so we've got those two factors, but they are each power 2, so we should try to see if we can factor them a little bit more, and hopefully these ones are not too difficult for you to factor. X squared minus 25 factors as x plus 5 and x minus 5. X squared minus 4 factors as x plus 2 and x minus 2. So now we can tell what the real zeros of our function are. They happen at negative 5, positive 5, negative 2, and positive 2. So let's mark those over here. And now using that end behavior that we decided on a minute ago, we can sketch our graph. We're expecting it, again, no multiplicity, so we're expecting it to just go up to infinity through each of those. It's going to turn around. Whoops, I missed. And something like this. This is our sort of W-shaped polynomial. All right, so that is the graph of this function. All right, I want to talk about one more small thing. This one's more conceptual than anything else, but we've been dealing a lot with polynomials, and you may have noticed, and we've talked about it before when we were solving equations, but the fact that this is a degree 4 polynomial tells me that it has 4 roots, and these ones happen to be real, and I can see them on the graph 1, 2, 3, 4. This is a degree 3 function. We have this theorem, the fundamental theorem of algebra, that tells us it has 3 roots. These ones happen to be 3 real roots. We can see them on the graph. Same with this function. It's a degree 3 polynomial. We can see the 3 roots. We can see 3 of them in part because we know that this root is a repeated root and has a multiplicity of 2. So the fundamental theorem of algebra guarantees that the number of roots of the polynomial is equal to that degree. However, that number of roots, that's in the complex number system. That means in this entire number system, we're guaranteed that number of roots. Well, a lot of the ones we've been dealing with lately have been in this group. They've been real roots. But we could have roots that are irrational or that are having an imaginary part. We call these ones non-real. So if we had a root of 3 plus 4i, or 5i, or negative 2i, or 1 minus 3i, those are non-real roots. So even though the fundamental theorem of algebra tells us how many roots or solutions we're going to expect, not all of them are going to be real. If it has real roots, we will be able to see them on the graph as x-intercepts. But the non-real ones, the ones that have those imaginary parts, they aren't shown on the graph. So I want to teach you how to look at a graph and tell how many of the roots of that equation are non-real. So when you look at a graph, you can automatically tell the number of real roots. This one, I can see 3 x-intercepts. That means it has 3 real roots. You can see the real roots on the graph. Well, the fundamental theorem of algebra tells me that since this is a degree 3 polynomial, it is going to have exactly 3 complex roots in that entire complex number system. Well, if 3 of those complex roots are real, that must mean that this function has 0 non-real roots. It has 3 roots, all 3 are real. I can see all of them. That means that it does not have any non-real roots. The number of non-real roots is just the difference between the number of roots that you know it has from the fundamental theorem of algebra and the ones that you can see on the graph. It's the difference between those two numbers. So let's look at this one. This one is degree 6. I know that because I told you. So that means that we know for sure, because of the fundamental theorem of algebra, that it has 6 complex roots. Well, now I want to see how many of them I can see on the graph. Well, I can see 2, but this one has that little terrace behavior right there on that intercept. Now what that tells me is that I know it has a root of -1, and I know that it has a root of 4 that's repeated 3 times. That is a multiplicity of 3. So I know that it has 4 real roots. Again, I know that because of the behavior right here. So if I'm counting up multiplicities, or if I'm counting up real roots, I would say that that represents 1 real root, and that represents 3 for a total of 4 real roots. Well, because I know it has 6 complex roots and I can only see 4 of them on the graph, I know it must have 2 non-real roots. The non-real roots don't show up as x-intercepts, but they definitely affect the behavior of the graph. They're an important part of the graph. In some ways, they're what's giving it this shape here, but they affect the shape of the graph for sure. All right, this one I know is degree 5. It's a degree 5 polynomial. That means we know it has 5 complex roots. Complex roots is the total number of roots. This one has 5. If I look at the graph and count up how many roots I can see 1 root here, and this root has a tangent behavior, so I know that counts as 2 roots. It's a root that has a multiplicity of 2. So that means what I can see on the graph is 3 real roots. And because I can only see 3 of those 5 roots, I know it must have a couple of non-real roots. There's 3 more for you to try. I would encourage you to pause the video and try it, and then check your answer. This is a degree 3 polynomial. It has 3 complex roots. I can see one of them right there, so it must have 2 non-real roots. This is a degree 6 polynomial. I know it has 6 complex roots. I can see 1, 2, 3, 4, 5, 6 of them. So this one has no real roots. Now again, I knew this one was multiplicity 3 because it has that terrace behavior. I know this one is multiplicity 2 because it has that tangent behavior. This one goes straight through, so I know it has just a single multiplicity, just a regular factor. All right, last one of these. This is a degree 8 polynomial, so I know it has 8 complex roots. I can see 1, 2, 3, 4, 5, 6 of them. I wrote 6. I meant to write 1 because they add up to 6. Sorry. I'll change that to a 1. 3 plus 2 plus 1 is 6. 3 plus 2 plus 1 is 6 here as well. And since this was a degree 8 and I can only see 6 real roots, I know it must have 2 non-real roots. Now I don't know if you noticed, but all of these functions either had 0 or 2 non-real roots. Now that's not always the case. You could have more non-real roots. You could have 4 non-real roots. You could have 6 non-real roots depending on your function. But it is always going to be an even number. And the reason that that is the case is that the method we use for finding those non-real roots is the quadratic formula. And because that quadratic formula has that plus or minus symbol, they always come in pairs. So remember, the quadratic formula gives us these solutions: negative b plus or minus square root of b squared minus 4ac over 2a. It's that plus or minus that causes these to be coming in pairs. So for example, if you had a root of 3 plus I, you would also have a root of 3 minus 4i. Anyway, the point of that is that we will get into this later, next unit. I sometimes like to whet your appetite for what's coming up. But what you should get out of it now is that this number of non-real roots should always be either 0 or an even number. If it's not, then you might want to check your work because those non-real roots always come in pairs. You either don't have any or you have an even number of them. Okay, last problem. F of x is equal to x to the third plus 3x squared minus x minus 3. I want to sketch, this time, the function f of x plus 4. We're going back where we started. So if I have this function and I want to sketch f of x plus 4, I'm going to think of the location of those intercepts, and I am going to shift them up 4 units. So they would now be up here. Now think about the max and the min of that function, the relative max and relative min, so that I can kind of get a little bit better sketch. And now that I have those points marked out, I could make a pretty good graph of that. Let's call this new function g of x. Well, I want to know the equation for g of x. Well, how I got this equation is that I took the original function and I added 4. So our equation g of x will just be the equation of f of x plus 4 more. It's going to be x to the third. It's going to be a 3x squared. It's going to be a minus x. And then if we combine these two terms, we find that it has that final term of plus 1. That's the equation for this function. How many real zeros does g of x have? Well, I can see that it has just one real zero. How many non-real zeros does it have? Well, the function is degree 3. I can only see one real zero, so it must have 2 non-real zeros. And the final question is, what is the y-intercept of g of x? It can sometimes be dangerous to rely on your hand-sketched graph for that, but if you maybe use your sketch and the function you wrote, you can see that the y-intercept is at 0, 1. Please try to remember when you're writing your y-intercepts to write them as points in general. And there it is. That is our last problem of the day. So next time we are going to be reviewing for the test. So you should now know how to write an equation from intercepts, how to factor pretty much anything I throw at you. You should now be able to understand how to graph polynomials and transform them. You should be able to identify the zeros or roots of an equation. You should be able to look at a polynomial graph and tell how many real and non-real zeros that it has. And you should be able to sketch the graph of a polynomial function from its intercept form. So that's a lot of things, but they're all so closely related to each other. Make sure that if you're behind on your homework, you get caught up on it, because the test will be super soon. Be ready for it. Thank you.